Okay, so why do we care about intermolecular forces? Well, intermolecular forces, or the attraction from one molecule to another, is going to tell us a lot about some physical characteristics and even some chemical ones. So let's take a look at some of the physical ones. If I have a molecule with stronger intermolecular forces, I'm going to have something that has a higher melting point and boiling point, higher surface tension, capillary action, viscosity, higher heat of fusion, heat of vaporization. The only thing it's lower on is vapor pressure and volatility. So if you think about gasoline, gasoline is actually very volatile, has a very high vapor pressure, very weak intermolecular forces. So if you ever get out to pump gas and you get back into your car, which they tell you not to do, if you do it though and you get back out, you just want to touch something like the car door metal to ground yourself before you go over to the gasoline, because gasoline is very volatile. So we said here this is going to be weaker intermolecular force. A weaker intermolecular force is going to lead to lower melting point, boiling point, lower no surface tension, capillary action, viscosity, low heat of fusion, heat of vaporization. It will lead to a very high vapor pressure at any given temperature, and it's extremely volatile. So like gasoline, if I were to have gasoline in a container, I would want to be really careful with that. Okay, so all right, so phase changes are going to tell us a lot about what we're working with here. If I'm going from a gas to a liquid to a solid, in a gas, the intermolecular forces are broken. There is no attraction. But if I cool them down, remove some heat from the system and cool them down, the intermolecular forces are going to start to attract. We're going to go to a liquid where you do have a fixed volume. The molecules are pretty close to each other, but it's still pretty fluid. If I remove even more heat, cool it even more, the intermolecular forces attract even more, and we have a fixed volume and shape. They're still vibrating, but they're pretty fixed. Now going in reverse, if I have a solid, I'll heat it. Average kinetic energy increases. My intermolecular forces are weakening. And then if I come over here and talk about breaking them, I just add some more heat and make sure that those intermolecular forces are completely broken. It's in the gas state because the average kinetic energy has increased and they've broken free from each other. So you should also take a look at the heating and cooling curve for water on page 522. Oops. And what we see here for the heating cooling, not a very good graph, but check your book. These are flat areas. Okay, so at 0 degrees Celsius, what happens here is we have ice, a solid, and this, by the way, is temperature, and this is energy. And so as we start heating this, we see that there's this flat area here where the temperature is not increasing. Energy is still going into the system, but the temperature isn't increasing. What's that energy going into? Well, what it's going into is weakening the intermolecular forces. And so what we have here is an equilibrium between ice and liquid. And this is called heat of fusion. And at the end of this, now it's gone all the way from here it's all ice and here it's all liquid. It's gone from ice to liquid. Now we're just looking at liquid. And now the temperature starts to increase. So I keep adding energy. The temperature increases until we get to 100 degrees. At 100 degrees Celsius, we have this equilibrium between liquid and steam. And it's going from all liquid to all steam at this end. But again, we get a flat area, which is longer than this area because we actually are going to break the intermolecular forces. Not just weaken them, but we're going to break those. And this is called the heat of vaporization. And at the end of this, what is going to happen is we're going to have all steam. So steam burns can actually be way worse than just a boiling water burn, because right, with a steam burn, it first of all can be a lot hotter, but also this giant chunk of energy right here, this chunk of energy is being released, and it condenses on your nice cool skin, but you get that big chunk of energy, and then of course any temperature change here, all that heat and energy. So a couple things to notice. Again, this is a longer curve or a longer plateau than this because we're breaking versus just weakening. But the other thing is, the stronger the intermolecular forces, the higher the heats of fusion and vaporization, both of those will be. It'll just take more energy to weaken and to break these. Let's talk about vapor pressure in a closed container. If we have a closed container, some of these molecules are going to be able to get out, and they're going to go from a liquid to a gas. But because it's a closed container, it's going to start getting pretty crowded in there. And then once it starts getting really, really crowded, they're going to start going back into, they're going to get caught and get pulled back in. So at any given temperature, some of the molecules will escape. And then when enough escape, it's getting kind of crowded, they'll get to the surface, they'll get pulled back in. A dynamic equilibrium is soon established. Think about like the target center coming and going constantly. And anytime one escapes, one comes back. So it's an equilibrium, it's just a dynamic equilibrium. The stronger the intermolecular forces, the weaker the vapor pressure, because the stronger that you are, the more you're going to be able to hold those in and it won't go to the gas state. The weaker the intermolecular forces, the higher the vapor pressure. So for instance, we have two things here, water and ethanol, or methanol, I'm sorry. And what we see here with water is we have 2 hydrogen bonds. Here, we only have the 1 hydrogen bond right here. So it's polar, little V-shape, V-shape, polar, 2 hydrogen bonds versus 1. So this is going to have the stronger intermolecular force, and it will have the lower vapor pressure. This will be weaker intermolecular force, and it will have the higher vapor pressure. Okay. If we talk about the next two here, we have 1 hydrogen bond and another hydrogen bond, so they both have 1 hydrogen bond. This one is bigger. Okay, so 1 hydrogen bond going here, 1 hydrogen bond going here. So far they're equal there. This one's bigger. This one's going to have the stronger intermolecular force and therefore the lower vapor pressure. This one is smaller. It's going to have the weaker intermolecular force and therefore the higher vapor pressure. Boiling point, we have a substance where the molecules have enough energy to break free from those intermolecular forces. Therefore, strong intermolecular force means a high boiling point. More energy required to break those intermolecular forces. Boiling happens when, because stuff evaporates, right, all the time, goes from a liquid to a gas state. And the vapor pressure we can measure in a closed container. And as long as they can break away from those intermolecular forces, their other molecules, and they can push against the atmosphere, it will form a bubble. The bubble contains the same, so if it's water, it's got water vapor in the bubble. Okay, it doesn't break apart chemically, remember. And if the vapor pressure of the substance equals that atmospheric pressure, then we are able to boil. So if there's less atmospheric pressure, for instance, water has a boiling point at 1 atmosphere, 100 degrees Celsius. But if you go to Leadville, Colorado, it's going to boil at 90 degrees because there's just not as much atmospheric pressure. You're up higher. You could boil water at room temperature as long as you remove much of the air pressure. If you're on top of Mount Everest, I understand you can boil water at 70 degrees Celsius. There just isn't the air pressure there, and the vapor pressure can push back easily. Surface tension, real quick, there's an idea of it here, of how it happens, but surface tension is caused by the high intermolecular forces because they're sticking together. Water bugs skitter across the surface of ponds because they take advantage of that intermolecular force, those water molecules sticking together. If you add soap to that, it actually does break the surface temperature, or surface tension, I'm sorry. And so pollution in lakes leads to a decrease in water bugs, which leads to a decrease in fish. Everything has an effect. A couple of others to mention: a capillary action. High intermolecular forces between molecules cause the molecules in the tube to climb the walls, stick to them until gravity counterbalances it. So what we often see is this, where the high, this is the liquid here, the high intermolecular forces are attracted to the glass, which is also polar, starts climbing up. The next one next to it starts climbing up, and the next one, and the next one, and the next one, until gravity pulls it down a little. But you'll see this, you're supposed to read the bottom of the meniscus. You're supposed to read the bottom of that, because that volume right there isn't going to matter much, and this is really where you should read it. You will see things that don't have much of a attraction to glass at all, and you can actually see something like this with mercury and that kind of thing. You actually read the bottom. Viscosity is a measure of a liquid's resistance to flow, and again, high intermolecular forces give rise to high viscosity. There's also another thing going on there. Large molecules also get tangled up and make the fluid viscous, so there's always a couple of other things going on, but generally speaking, those two are related. And that is it.